Yes, okay. All right, theory says I'm live. Form now. Okay, so this is Coffee Compiler Club, and you're all being recorded live, and theory says I'll get the next YouTube video out faster. I got this one out like seconds ago. I was already clicking away on the keyboard. Yeah, anything to do with compilers, language runtimes, garbage collection GC, locking, security holes, sandboxes in the kernel, history of computing. I just don't have to do too much history, but it's kind of fun. Oh, here's Zen too. We got another one piling in. I think that's done with my spiel. So anyone want to start? We're all good. I think everyone's been here a bunch of times. And I keep getting new people who want to join and then never make the first connection. So first time in. Yeah.
That's sad.
Yeah. Let me fix my video a little better.
Calendars are hard.
Yeah, but then I can't change my time because everyone else has to deal with the time change for them as well. So you hit a quorum and people have scheduled their times around, and then I just can't be flipping it for somebody else. So that's the current state.
The time switch is going away, I believe.
Yeah, the time switch. Oh, you think it's going away in general?
Yeah, each country has to decide in which time zone will stay.
Yeah. Or in the case of the US,
we just need to get rid of time zones.
So we are living 2 years in a row, but hopefully.
There's a thing called like a Swiss watch internet time or something, where they count it in like beats or whatever. It's like a clock on a scale from like 0 to 700 or something.
No, I just search for the time in Sunnydale in Google, and they tell me what the time is it, and I adjust.
Yeah, it's probably easier to announce the time as like Unix time, because then it's easier to convert to local time, because I also have to Google it every time what that's.
And every time I go to Europe, I have to Google it too. So I'm just like, okay, that's part of the steps. You hit the Google thing, doesn't take too long. Like these days, there are many things that I look up or do where the first touch is to go to the search bar in the browser, because it just doesn't matter. It's just too fast. I can't type any other thing than 5 characters of what I want in Google, and they'll have started guessing it already. Okay, done. Boom. Including time zone in, and then the options are appearing, and half of a city name and done. Yeah. All right. Enough whining about time zones.
Maybe picking up on that. For when building new languages, I often have the impression that there are certain topics like time and time zone and calendars and Unicode and a few other things.
Yeah.
It's basically every language has to more or less reinvent it.
I have to screw it up in a new different way.
Yeah, because it feels like there is no common ground implementation that is both primitive and low level enough that it's simply adopted as some general at least you can't even depend on it. It's like probably every Linux system has like a time zone database file lying around somewhere, but if you're writing a language runtime, you can't depend on it being there. You always have to ship with it, and that's also. So I'm not sure what can be done about stuff like this.
So in the case of Java, JODA time, JODA, is like the go-to package. They got it right. Like not the JDK, JODA. It's low level, it's fast and efficient when you want it that way. It has all the right bells and whistles. They have all the right defaults. Go get JODA time.
So what did the JDK time package get wrong?
Oh, they had a bunch of things wrong, and I bailed out on it. Let's see here. I had a very fun comment in one of my H2O, like go parse times out of data sets. Go do fintech with times with every exchange and everything. So you have to deal with time and time zones and things that were not labeled with time or whatever. So the first one was the core structures to convert from one kind of time to another, to convert time zones, were not multi-threaded save in the beginning. So that if you have multiple threads saying take a current time in this time zone and convert it to that time zone, they would fight. So then they started throwing synchronization in, and then they became scaling bottlenecks for people who had to do large volume time conversion concurrently. And then they started having races that threw exceptions. So I have a list. Where do I find it? I have a list of 5 exceptions I got out of running concurrent time while parsing time files for H2O that I could get all at the same parse file. It was all at the same time.
Okay. So what does JODA time does differently?
The basic time unit is essentially a long, which you can then wrap if you want to, and it's wrapped persistently. And then all the internal conversions, left, right, up, and down, are all multi-thread, concurrent, safe, and efficient. They're all immutable. And that's a case for immutability. I go back and forth. Some things need immutability, some don't. Some have to be concurrent, yada, yada. Time should work with immutable shit, and they did it right. And it's,
okay, because I had the impression that the JDK time stuff was more polished, because like the author was the same, and I think it took a lot of lessons learned from JODA time and implemented it.
JDK time got improved over time. I have used JODA for a long time. And if you're going to tell me there's one and the same, I'll have to go stare, see if this is new and different. But it was certainly the case as of only 5 years ago that time was like an issue, the JDK time here.
Okay.
Here's a comment I have from my H2O source code. I tried Java util simple date format, just throws parse number format array index.
But that's
in Gregorian.
But that's not thread safe, but it's also not related to the JDK time package. It's like one of those.
Date format?
Yeah, it's from Java 1.0 or something. It's like, it's broken.
When I started on H2O 5 years ago.
Sorry?
It was the known default when I started on H2O 5 or 6 years ago.
Of the default for what?
For screwing around with time. Go parse time. Here is a wad of text. Convert it to a time value.
Okay. Yeah, that's
not
sure.
Roll your
I think
clock back a few years and ask what was the default go to. Like I had to deliver this to clients who at that time were on Java 6, and I
sure.
It to Java 8 a little bit later. But I had to deliver on Java 6.
Sure. If you're below Java 8, then go for JODA time. Sure.
Okay.
But after Java 8, just use JDK datetime formatter.
I believe they based it on JODA time.
Yeah.
The 8 implementation.
Sorry.
I believe they based the default JDK implementation on JODA time.
The author is the same. It's from the same author.
Okay.
Stephen, I think Stephen Colburn or something like that. It's his name, and he wrote JODA time, and based on the lessons of JODA time, he implemented the Java time, and he still have like this BSD licensed implementation lying around from before it was migrated to the JDK, which is extremely helpful if you need like a decent time implementation for other languages. So maybe 5 years ago, I converted the whole Java.time package from Java to Scala to be able to convert it to JavaScript and native code and stuff, and it worked perfectly fine. So that's really nice.
Yeah, the JODA website now says if you're on 8 or after, go use Java time. Which just still goes to your point that it's really easy to screw this up.
Yep.
And a lot of people do.
Yeah. It's always totally crazy how much of the time stuff, how much of the lines for time processing is actually spent in formatting. It's totally crazy. It's like if you throw out formatting, it's like half the size.
Yeah.
It's not, yeah.
That's not a new thing. The people that found that ridiculously complicated box of gears in a boat from like the year 1000 or whatever, and they looked at it and it's like, well, about 25% of the gears are tracking the movement of the sun and moon and stars, and 75% are getting it into the timestamps of the day.
Oh, yeah, maybe. Sure.
And it's like, oh, it turns out even then the months didn't all have the same number of days in it. So
yeah. And yeah, that's the one. I just watched a video on that like yesterday or the day before. They have more things now. They got really good 3D imaging on the interior of it. And they found all the gears and did all the alignments right. And you know, they have to do shit like divide by 19 and multiply by 17 and all kind of prime number things going on in there. It's an amazing piece of work. And more amazing by its time and era. Like even modernly, it would be a fucking amazing piece of work. But you know, 2,000 years old, holy shit.
the JODA time of its day.
Yeah.
Yeah, I had the pleasure of having to implement a not so much a time library, but a time class for my programming language, because I wanted it to not be tied to the host language, in this case Rust, and that's largely because the time type that Rust provides in the standard library is fairly limited in what it can do. And there's a couple of libraries, but they all pull in like a ton of stuff like TC databases and stuff like that. And so I basically went looking like, okay, you know, I can use a system call, whatever, to get the timestamping UTC. But is there sort of a, I would say, approved way of breaking that down into the individual components, like year, month, day, etc.? And I ended up having to, well, the answer to that is basically like, no, there's no clear thing.
But JODA time does, or Java time now.
So there's libraries doing it, right?
Yeah, right?
There's plenty of libraries doing it, but it's no, it's not like you can go to Wikipedia, for example, and there's, you know, an algorithm that says, here's how you do it.
Well, yeah, we just got the link hit right here. No, there's no.
Right. And so what I ended up doing is I believe it was from the Muscle C library. They have a function, I forgot which one it was, where they take a timestamp and break it down into its components. And I basically stole that algorithm because it was actually fairly readable and quite easy to port, and you know, not riddled with macros.
Almost surely wrong in any number of weird corner cases.
Oh yeah, so it doesn't handle anything before 1940 whatever, when the calendars switch, the usual one. Specifically before. Am I saying this correctly? Because it is based on Unix timestamps. So before 1970, it gets a bit fuzzy. But then I think it's like the 30s or 40s, there was some calendar switch too. And it only does, you know, modern day calendar.
Right. I've been, you know, read it up like go find the computation for when Easter lands. And it's like the third Monday past the last full moon of the spring or something ridiculous like that.
Yeah.
And of course, it's a bizarre ass calculation that you cannot.
It's basically, from my understanding, basically if you know, let's say take the 1950s and you go further back, it gets really bizarre. Like it basically, and you need a special purpose library.
Interjected time gaps to catch up. Solarian time with whatever lunar and seasonal and all that kind of shit, because they had like drift for a long time, and the, you know, the leap second, leap day thing needed to be corrected, and the corrections on the corrections and epicycles on our epicycles.
So at the risk of changing the topic,
yes, please.
In H2O, how do you give the actual work that you want done to each of the worker nodes? Because like in the old Corba days, you sort of had to run the same binary on all of the worker nodes, and you would just send a serialized class and it would be like, oh yeah, I have a constructor with that name.
Yeah.
But like you have a lot of flexibility in JVM. You could throw bytecode at it or actual code at it, or.
So the first cut is everyone launches the same jar file. And then we Paxos up, and as part of the Paxos up protocol, we ask each other that we all have the same jar. The assumption being the same jar, where the same class names will map to the same goodness bits. After that, we could, and never had to, but we could pass around raw Java text as a new class file. So you could class for name that way. Instead, all the classes that you were running at the moment were already passed around in that one jar that you started up with, but we could pass a jar file around. We had times and places where we passed jars around. There was certainly a version where we would load code on one guy and pass, and I said jar or Java text, we pass around class bytes, literally. In fact, that might actually still be there. Yeah, we pass around bytes, but we give you a new class name, and then here's your byte codes. So that it was guaranteed unique from whatever other byte codes you might have. So we played a name to make sure the namespaces were safe, and then here's your code.
You relied on the namespaces. There was no game like, please construct the class whose SHA is this.
No, we guaranteed uniqueness of the names. So the first thing happens is the core jar, the base jar was the same. So those names are all known, unique, and sensible. Then we made sure that user code was in a user code namespace, but then we passed around bytecodes where your namespace was unified, however that was done, and then you started executing that. Does that answer your question?
Yeah, I was just curious what design trade-offs went into that, because it means you have to know before you start what's the list of classes that you're going to end up launching. So you could imagine doing something that's like, hey, I've just got H2O running on some web server and something connects to it. It's like, here's a job, please distribute it to everybody.
So, right, H2O is a peer-to-peer big data server, if you will, big execution, big math server. And as part of peer-to-peer, typically everyone runs everything. And an asynchronous model where some node is faster than another because one's running in a browser and one's running native wouldn't work well because I didn't have any heuristics to handle it. So everyone had to be running the same performance levels. Fine. Okay, so now that you have these nodes up and they've talked to each other and they've agreed that they're all agreeable, if some node gets handed a wad of code and you say, go execute, he can go hand it to other nodes. So the first thing happens is, I have a job for you. Well, that job is serialized into wireline bits. The headers are, here's a descriptor, which is eat these bytecodes and load them as a class file because work comes with them shortly. And that's a known task that already exists on all jars. So I serialize a class that has a byte buffer, which is another class, send it over to the other dude who reinflates the outer class, executes the run me code, if you will, which turns around and says, take this other guy and, you know, load him as a class, and here's his name. It's been unified already. However we did, like I said, however we did that got complicated. And then I'm ready to go eat an instance of this other class. Then the node you started with, you usually said, make me a new, Cliff Click class instance, populate it with whatever you're going to populate it, generally pointed at big old pile of data over there, and run the do all, run the map reduce, run the whatever the thing is. And then that gets shipped around the cluster and you go from there. So it's definitely a way to do it.
Distributed the functions locally where the data are optimally. So you send the functions to the data, not data to the function.
Yeah, the assumption is the data is too big to be moved. It's too big to fit on one node. That's the reason you're a cluster in the first place. So the code has to go to the data, not the data to the code. And furthermore, the functions can only ask about data that's not on their local node in a very limited way, or you'll run out of memory and die because it just doesn't fit. So there was a coding style that allowed you to conveniently talk about the data that was local on your node, and inconveniently talk about data that was, actually fairly conveniently talk about data that was at the edges of your own data that would have been a little bits on each of the nodes around you. But if you went and said, please get me all the data from all the nodes, you just die.
So locality of the data is it has been prioritized.
It has been strongly encouraged by design of the coding style that the data was highly local. That's right. So basically, I said you had a big array and you did a for loop over the big array. And under the hood, behind your back, I split the for loop up into a bunch of little arraylets, one per node. And you ran a for loop on your node's worth of data. And then because it's a map reduce, there was a paradigm that lets you talk about data that was the summary from all the other nodes. You produce the summary, they all produce summaries and so on. And that was recursively down several layers within a node and all that. Oh God, well, we're a little ways off yet from colonizing, orbiting different stars. So I'm not too worried about that one in my lifetime.
No,
Lifetime.
I think that falls in the category of, for most cases, using, I would say 32-bit integers for most timekeeping purposes are correct, but 2031, I think, is coming pretty soon.
You think 64 bits or 32?
Well, that's 32.
Yeah, 64 bits aren't that expensive. Just use extended time.
Right.
So what about Star Wars Star Date? Was it?
We mean from a 1960s TV show?
Yeah, Star Date 62.5.11. Just kidding.
Well, and maybe then we'll wrap up time, because that's, I think, a topic where a lot of people need a lot more drinks. But I've always believed that the Stardate system that they keep is broken because they frequently travel at faster than light speeds, and time being relative.
Yeah.
And they note stuff down while traveling faster than light. So it's like, yeah, anyway, you shouldn't think too much about that probably.
No. As soon as you break one laws of physics, you got to break them all, right? It's Lay's potato chips. You can't just eat one. Fine.
Okay, next question. If you start a new language, what representation for strings you will choose? UTF-8, UTF-16, UTF-32, something else?
Oh, that
depends. Do you work at Microsoft or not?
So I would certainly default the source code to UTF-8.
That's not a bad answer. My underlying representation is going to be a fucking array of bytes. Having fought so many string implementations that were not a fucking array of bytes and had them be wrong and horrifically slow or buggy in all kind of ways, no. Fucking array of bytes. Okay, thank you very much.
Encoding then. This array of bytes does it encode the code points as UTF-8, UTF-16. Now anyone I know who doesn't use UTF-8 says they regret it, but UTF-16 is not that much worse. It's often not worth the change from 16 to 8 if you already have a UTF-16.
No, but what happens is I load a terabyte of data from a CSV file, and it comes in as bytes, and I do not desperately want to double it to 16. Okay, now put an encoding on it. UTF-8 is a fine encoding. And if I want to have a null terminated C string, and I want to have a UTF-16, I want to have a these are all not the core string, but they are some convenient other thing. So there's like stir as a string that has whatever encoding of the joy of the day, which is byte-wise only. And then there's ustir, which is Unicode encoding with whatever Unicode 16 or however you want to go it. And cstir for null terminated C string compliance. This is a Python just got it pretty good.
Yeah, that's what Rust does.
But the default will be an array of bytes with some reasonable default encoding, which UTF-8 is good.
So Yorick, what representation of strings you choose internally?
So Rust, they have a couple of types. So they have string, capital S. That's for whatever reason, resizable string that uses UTF-8.
Not resizable string.
Yeah, so this one is resizable.
Right. Mine is going to be that there's a separate thing that says I have a string builder, a string maker.
I would agree with that. I feel strings should be immutable for various reasons.
Yeah, I think in the Rust case, it's more or less a problem with naming. That the naming doesn't make sense.
Yeah, but so you have capital string. They have string slices, which are immutable, and they are
but the capital string is resizable.
Yeah,
and therefore the string body is immutable. And
so capital string is resizable. It's basically just a wrapper around a vector of bytes.
Right.
A string is basically a string buffer in Java.
Yeah, it's appendable, or it's like full-on mutable, change any.
Full-on mutable, like you can pop, push, whatever.
So, because a slice is immutable, told me that you're having an immutable slice over a mutable string. How does that work about making a defensive copy?
So you can have a string slice to a mutable string, but then through Rust's ownership system, if the string is immutable, you can get immutable reference. If it's already mutable, it will say no.
Okay.
because the mutable references are
so the slice
exclusive.
is either unavailable or it is known to be mutable or known to be immutable as part of the typing system.
No, so when you have a slice to a string, it's basically guaranteed that that string is immutable.
Okay, so
at
it's
least
unavailable if the string was already mutable.
Yeah, you can't. As far as I remember, you can't get a slice from it then.
Yeah, that's fine.
But then they have a type for C strings, which is called C string or C str with capital CS.
Yeah.
And then they have a string that represents the sort of native operating system string type, which is OS str.
Okay.
Horrible to pronounce.
Right.
And that's where you get these sort of weird differences where on, say, Linux, those are all more or less the same. On Windows, OS string is UTF-16, but string is UTF-8. C string is, well, C, so just bytes.
That's a pile of bytes with a 0, yeah.
Yeah, so you have to deal with all these conversion troubles if you want to do that.
Okay. Does the OS string include file name dorking operation?
Yeah, I think anything that's sort of from the file system is returned as an OS string.
Gotcha.
And you then can convert it to UTF-8 if you want.
Yeah, you tend to need that on Windows because the Windows file system strings are basically UTF-16, if I remember correctly, except that there's the like upper half of a half word and lower half of a half word, and they don't check that they're next to each other. So you can just stick a random half of a character in the middle of your file name, which is not valid Unicode, but is valid Windows file system string.
Excellent.
So it forces you to have a new kind of string because sometimes when you read the file system, it wants to hand you back a string that's not valid Unicode.
Gotcha.
I think from the Rust or Mozilla space also comes this WTF8, which is more or less UTF-8, but allows encoding of invalid UTF-16, I think, code points, so that whatever broken thing you get from whatever kind of native API, you still have some way of encoding it in some UTF-8-like fashion. So it's still in the end a pile of bytes, but with a bit more tolerance. And I think that's also interesting. I think it's certainly a valid choice or consideration to make for basic string type, either like UTF-8 or WTF-8. But yeah.
So UTF-8 wins.
Yeah, it's like yes.
For my opinion, it's because ultimately it doesn't inflate what you read off disk, and as an array of bytes, I can do shit like Boyer-Moore search algorithms and stuff like that on it, and it will work as expected.
And you don't have to deal with byte order marks, which is like it's like the times I've not only had to deal with byte order marks in the beginning, but also in random parts of the file because people just stitched it together. It's like, no, I never want to deal with this again. Interestingly, I think this language server protocol, because it comes from Microsoft, specified the use of UTF-8 of UTF-16 in some places for like offset or something, and it was funny to watch that people just decide, yeah, well, we are not going to do that. So screw it. We're using UTF-8, and yeah, it's like we have this some kind of way to check it, but if you don't check it or don't support it, then well, you get UTF-8 offsets, and you can deal with that. So, and that's quite funny. It's like certainly a move in the right direction.
There's a whole bunch of clients that did that wrong. I saw the discussion as well because at some point it's like, how difficult is it to implement a language server? And overall, it seems like fairly enterprisey, as in, there's all these basically a ton of interfaces. Everything is like verbs or whatever in the name. Anyway, then I reached this offset thing, and it's been a problem for like 6-7 years where people have been asked like, hey, can we, maybe start, a new protocol version, but make it UTF-8. because there's no reason for this to be UTF-16, because everything else is UTF-8 in the protocol. It's just that offset thing, they use UTF-16. So the source code that it processes, UTF-8. So it's this inconsistency, and there's a bunch of clients, yeah, that, like you said, they've said, like, we're just not going to support it. Too bad. And I think there's one written in Vim that I recently saw where they had to go through a bunch of hoops to deal with this because Vim doesn't really support UTF-16. It's just one of those things like, just use UTF-8.
Okay, I think we settled on it.
So if your array of integers is not code points and you just need a generic array of variably sized integers, what do people reach for?
Array of bytes or array of variable sized integers?
An array of variable sized integers.
Why do I need an array of variable sized integers?
So a lot of databases reach for that because you've got like a whole bunch of integers and the vast majority of them are tiny, but some of them are giant. So you don't want to necessarily use int64 for the whole array.
In the land of H2O, I do compression and I don't care. My API is always 64 bits, but after the load through the compression strategy, it peeled from bytes or ints or shorts or I don't know what, bit encodings and run length encodings and everything else. So that's the large, dense, columnar compressed format version of the world. It's all 64 outside of the physical memory storage.
Yeah, that's sort of my question. When you're writing out to physical storage, what is your dense columnar format for a bunch of integers?
It's compressed.
GZIP, yeah.
Now, what is the compression strategy? I break you up into arraylets and I look at the local version of the arraylet and I pick one of 20 strategies. Depends on now.
By just doing all 20 and seeing which comes out smallest?
Yeah, yeah, pretty much. You run a heuristic through it. You run a counting pass once through it, just to count ranges, upper bound and lower bound, and bending this and that, and offset games. There's a bunch of passes you make, not passes. There's one pass and you collect a bunch of stats. Then you look at the pile of stats and you can quickly just choose, oh, this is actually integers and not floats or doubles or weird mixed things. Okay, out of the integers, it has a range like this. Okay, now I can go to a narrower range. If the histogram says I only have, I have one dominant value and many scattered other values, maybe a run length encoding where I encode the empty spaces as the run length of the non-dominant or dominant one, right? So the common case, it's all zeros except the occasional one, or it's all NA for missing value except the occasional real value, right? So there's a dominant guy. You do the dominant versus not. You do long runs are the same thing. You do lower bound, upper bound's pretty narrow, and I can start with a base and add an offset. Maybe with the shift and offset, a common scaling factor is 10 because I'm doing money. And so I have scale by 10 and then 2 digits or 3 digits or however many digits past the decimal point, all that kind of shit. Those are all run, you have one pass, count them all, then you run through some heuristics to pick which one you're going to do, and then you second pass to go do the compression. And that's pretty much what the H2O parser does upon reading the data in. It has a pile of bytes, it turns them into a pile of longs, and then it says compress the shit out of longs. There's a few other odds and ends, but I don't think we actually have to have an extra yet again pass. I think it's all done in 2 passes. And I think, in fact, we do the other smarter thing was we start by jamming you into an array of bytes, and we inflate lazily as we see larger things to make you become an array of shorts, ints, and longs. You know, powers are 2 bigger until we get to the end and you're all 64 bits or whatever. But if you're all only bytes to begin with, you all stay bytes and we never blow you out. And that is so that we don't increase our cache footprint if you started as an array of bytes, bite-sized things. We don't pre-inflate you to 64 bits, but you might get there if you happen to have that size.
Does anyone that has a language implementation benchmark their lexer? How many tokens per second or something?
All the time.
So what is a representative number?
Well, that's a good point. So The AA parser, I don't have big enough text, but I know I touched characters mostly only once. Maybe there's an occasional second or third. So it's going to be memory bandwidth bound, as usual story. Plus, I'm doing typing while I'm parsing, so I can't bulk do things. Whereas I look at the H2O CSV parser, so tokenization is on field boundaries, which are getting lazily discovered. And sometimes you have funny strings, and sometimes you have quoted strings, and this and that, and other shit going on. Okay, that guy is almost always totally bound by the speed of your disk. And if you're in OS caches, it's hundreds of megabytes a second, headed for many gigabytes a second. If you're actually, it is well above a gigabyte a second if you're coming off of OS caches, now that I'm thinking about it. So somewhere between 1 and 2 gigs a second coming off of OS caches.
But isn't benchmarking the parsing step a measure of, or a sign of, like, you're not doing enough type checking if that's your slowest part of the compiler?
So if you're running a Java JIT and you're handed bytecodes, you have to verify somebody else did the hard work already. I'm not measuring Java C, I'm measuring how fast can I verify Java bytecodes. So it was interesting, compilers were pretty quick. So, verification couldn't be super slow. But it was a shortcut. I didn't do any typing, not in the classical sense. All I did was verify, right?
Would be interesting to see at which step verification locally is slower than having some kind of public key infrastructure signing step where you, like, after compilation submit, or if you like you publish things to main repository, they verify it and sign it. And then you say, okay, if I get it from the main repository and it's signed, I know I can skip the verification step during loading. This would be interesting to figure out.
That one is the cost of verification is low enough versus the risk that somebody hacks
that's
redirects your DNS. And
that's true.
I only have to do that once, and I robbed the core guts of Bank of America's security, because they ate my class file inside, and now they can't get rid of them because it's in their local Maven repository, caching. And now the bank vault just got opened, and I'm walking away with the money.
So you have to verify either way.
Yeah.
Without.
Yeah. You have to verify it every time. Sorry. And it's cheap. So what the hell? Just verify.
Yeah, I didn't measure my tokenizer per se. I did at some point measure my awfully written Ruby compiler. And this was largely because at the time I thought, hey, I want to see how much effort it is to get this running in a container so I can set up sort of an online playground for my language. Setting aside the whole infrastructure trouble of running containers and that sort of thing. I think, if I remember correctly, I found that time-wise, most of it was spent in just basically Ruby being slow and my code being awful. So kind of all over the place. Most memory was actually spent in code generation. Specifically bytecode generation. Because what I was basically doing, taking these Ruby data structures, strings, floats, etc., and sort of packing them into a series of bytes. And as part of that, Ruby would allocate extra arrays and all sorts of things.
Your problem is you're using Ruby.
Yeah, part of it definitely was the problem. Part of it is the lack of streaming APIs that Ruby has. So things like packing or unpacking strings. As to say this correctly, if you want to take a string and sort of convert it into bytes, for example, what you do is you take an array of string and then you do that, because packing operates on an array. So now you need to allocate an array for everything you want to pack.
Yeah.
And there's a bunch of other stuff there.
Where I start out by saying, and now you never, ever allocate per thing you're going to do.
Yeah. And there were some other things where I had to resort to just plain old bit shifting and things like that. And I think the saving I got, it went from like, 100 megs of memory in total for my own test suite to like, 40 or something like that. So it's a pretty sizable amount. But yeah, I would say most compilers, probably most time would be spent either parsing or type checking. And code generation, I guess, but that you could do in parallel fairly easily. It kind of depends sort of what level. If you have, say, everything type checked, you have your IR, it's basically ready to go.
Yeah.
Then you could, if your output is a single file, it's a little difficult. If your output is multiple files, it's a bit easier. For example.
Okay, so the compile boundary is typically somebody's method plus its inlines, whether you're ahead of time or a JIT. At the compile boundary, totally parallelizes. Works great, pmake, multiple compiler threads. Within a compilation unit, single threaded all the way. And most of the time is spent in the register allocator. So if I'm doing a dumber compiler, then you get a little more of a smear between dumb optimizer, dumb parser, and dumb register allocation code gen. If you're doing a better JIT version, it's like 40% in the register allocator and 30% in the what you might call the core optimizer. And code gen is like nonsense. It's down in the noise, and parsing's down in the noise. 5% to parser and 5% to code gen and 40% in the register allocator and 30% in the core optimizer, something along those lines. There's a few more bits floating around, but it's.
Which is funny because in the compiler course, you spend almost no time talking about the register allocator. They're just like, do something graph colory. Okay, moving on.
Yeah, right. And that is where most of your performance wins come from, that are, once you've done the basics of a core optimizer, so you've done dead code elimination, and loop invariant code motion, and constant propagation, common sub-expression, once you do those things, the next thing that you get performance out of is inlining, especially for modern languages, including Java. You want to inline the hell. And then because you over inline, you have to register allocate well. And so register allocation. And your performance wins come from being able to bump up inlining without having the register allocator die, or die, I mean, like just puke registers everywhere. And so that turns into a more clever register allocator, enables more inlining, which is directly tied to performance. So all your time is spent, or should be spent, in the register allocator doing a good job when you have over inline. And that makes that a big, expensive, hard to do thing. And you're right, the classes should be taught on that aspect of things. And back in the day when I took my compiler classes, we didn't have a class on register allocation, but we had a section. So I spent at least a month, maybe two, doing register allocations. We all did at least a couple variations of different allocators.
Yeah, I was going to add that, as usual, this depends from compiler to compiler, and in different compilers, the time spent, the ratios will be slightly different.
Well,
yeah, if you try to compile C, you're going to spend all the time reading the same header file over and over and over again.
That's really fast. Yeah, you think so. And if you read it from disk every time, and every compiler since like 30 years ago caches the hell out of the headers, does a checksum at the beginning and says, same header file, same bat channel, preload the the symbol table, and I already got ready to go. So.
Yeah, I have seen a blog from some guy, I don't really know, Sam Brett. He wrote on how to write a fast lexer as he knew it. He lexes 7.5 million lines in 0.23 in 2 seconds roughly.
Yeah, that's
yeah.
reasonable.
So this is representable, I believe.
Yeah. Like I said, for me, I touched the bytes once. It's all about getting it through the cache hierarchy. So you get 1,000 cycles per byte. Not quite. You get a couple hundred cycles per byte to do something sensible, because that's the cost to get it from memory to the core CPU. Well past what you need to lex it. Far more cycles you need to lex it. So I do a bunch of semantic checking as well while it's coming in. And in fact, your time there is spent, don't go in and out and in and out and in and out over the IR. Whereas the thing that, one of the difference between C2 and LLVM is just the amount of times that the IR gets touched, and that turns into big pieces of the performance. This is stream through.
Yeah, it was in relation to like compiler courses and such, what they dedicate their time to. It seems to be the same for books. It probably depends a bit on what book you buy, but usually the first quarter is like parsing, which is the most boring part. And most it's like, oh, by the way, we also have type checking this, that. Yeah, we're not going to bother. Now we're going to dedicate 500 pages to code generation, for example, or in other words, there's this weird imbalance where it's like these things are important. Right. We don't cover. This is also important, but maybe less. That we cover extensively.
Yes.
Yeah. I concur with that. Almost all the books ignore the type systems, which are hard, basically.
Yeah. And obviously very important.
Yeah. Let's say.
The language domain.
Yeah. Cool. Yeah.
Yeah. I have a question about regis allocation. Cliff, you said that in most of time, compilers spend like 40% of time on the regis allocation.
I'm quoting C2.
Yeah.
I mean, for C1 or LLVM.
Yeah, actually, I profile some kind of da couple benchmark and for C2, and I did observe the similar situation in the flame graph. So, and also I hear you that you said that the trick is you need to tune the regis allocation to not to fail in front of aggressive inlining. So out of curiosity, I haven't read all the source code of regis allocation of C2, but in my understanding, it's like a trading bricks algorithm. So what did you do to tweak your regis allocator to tackle the problem you mentioned before? And let's say that I can arbitrarily inline everything, and the register allocation won't fall into like terrible places.
Right. So this is a big topic.
Yeah, actually, you gave us like a presentation like 2 years ago, but you only mentioned one single sentence about this one, and there's no detail. Yeah, I really hope that you can describe what did you do in register allocation of C2.
Right. So this gets into the design philosophy of the register allocator. So in the C2 register allocator, I went with it's graph coloring, classic Briggs-Chaitin, and I treated basically all spill code as another register, one that you can only get out with a load or a store. And it has a cost, therefore, associated with the load or the store. And then I said, I'm going to register allocate to an infinite register set, some of which are more expensive to get to. And you make a go around at attempting to color. I guess I should back up to say that the benchmark here that you're looking at is if I had not inlined, I would have paid call or callie save register costs, call or callie save spill costs around the places where I failed to inline. And I want the register allocator to not do any worse than that, right? So if at the time that I do, the register allocation, if I come to the point where I'm out of registers, if I just looked at the points where I inlined a piece of code and I just spilled everything and then loaded for the inline and then spilled and reloaded in the inline, then if I'm no worse than that, then it didn't hurt me to inline. And of course, the inline boundary is not so sharp. It smears out everywhere and a lot of parts disappear. That's the whole point of inline in the first place. So it's not so tidy as that, but that's sort of the benchmark. Okay, so having said all that, when I go to do the register allocation, there's a first round of coloring, which always fails. But you have to try it, because out of the first round of coloring comes the set of edges and the live and the interference graph, which you can trivially color and you don't care about. So you clean them out. And you get the set of live ranges that will never color, typically because they have register constraints around calling conventions. This calling convention demands a register in RCX. This calling convention demands it's returned out of RAX. RAX is not RCX, it's just not going to color. You have to split the live range. Okay, so then once you decide that you have to split, you split all the guys. And when I say split, that literally means I insert a copy in the live range. And when I do the split, I stare at the block frequencies and insert splits around high frequency blocks.
Yeah, wait a minute. This is this kind of breaking of the live range, and doesn't mention in the classic trading breaks algorithm, right?
Oh, no, it's because of, well, it is, but it's not. It's when you do spill code, right? So for me, all things are live ranges. I don't have a memory home versus not a memory home. You can't in Java have a classical memory home. So I'm talking about terminology used by register allocators from 40 years ago. You roll it back to Briggs Chaitin, but you have to spill to the stack because the Java memory model says I can't reload or restore in and out of a particular variable except the semantically preserved set of times defined by the language. So spills are always to the stack typically, but I call the stack as another pile of registers. So instead of having stack slots that are spill code and registers, it's all just registers. But the stack registers,
special.
Yeah, there are registers that you can only get at with a move instruction, which is a load or store. And the load or store has a cost to it. So there's a cost model. So splitting a live range, and Chaitin will talk about splitting live ranges, is simply you insert a copy in between. And in my case, I always insert a generic copy, which might expand to a reg move, a no up if you kept the register on the same side, or a load or store. So the goal there was to enable the allocator to choose to go push it in memory or not, to a stack slide or not, but also to choose to keep it in a register, and also choose just to do a fucking move if that's all you had to do. So you go around again on the next round of spilling, having cleaned up the must spill register live ranges. And typically the count of the typical, after you remove all the trivial edges, the color requires one more color than you have registers, because you always get right up to the edge. So this is you're running an NP complete problem, an exponential problem. And so, you're doing a linear thing, so you have a heuristic, and you always asymptotically approach colorability. And you try to color again, and if you fail to color the second pass, and that's kind of common for any big compilation, you now definitely split everybody who's not trivially colorable, and you split them around all the high frequency places. So you look at all the loads and stores, all the use points and the def points, and you insert splits not at the def or the use, but at the next largest enclosing loop boundary outside, because you're trying to get some kind of good register allocation in the loops.
Yeah, I heard that you may have like multiple trials for the register allocation, right?
This is another pass. So it's another trial. If you
yes. And is that possible to make use of the internal results, like intermediate results for the last trial?
Every trial is also producing results that are reused for the next trial.
Okay.
These things are pipeline and overlapped in a funny kind of way, because you need to have two different versions of live ranges. You end up having an interference graph, and you have a bit vector and you have a graph form.
Okay. Yeah.
You end up with both at different times, and you end up ping-ponging with an overlap. So for one, you have one, and then you have the second one that overlapped, and then you have neither because you're busy spilling and recovering, and then you end up with the other guy again, and it bounces up and down. You get to use them. Then that's all in there already.
Yeah. Actually, there are like two different type of dealing with the coloring things. The first one is spill, the spilled value, right? The other one is remasterization. I don't need to spill it. I just recalculate them. So do you use the second choice?
Yes. There's some things that the spill instruction is I just took the root values and recomputed them, but that's done as an after pass to clean up. So the main coloring guy gets a coloring, And he gets it by continuously chopping live ranges down until, like, if the second pass where I break you around loops didn't do it, on the third pass, I break you very sharply.
What's the meaning of sharply?
Well, at every load, at every def and every use, the cat just like clawed in, clawed out, clawed in, clawed out, clawed me. Sorry. At every def and every use, and again at low frequency places also, just to keep things looser and looser, till I get a coloring finally. Once I have a coloring, I will come back and look and see if I can unwind some of the spill costs by doing a rematerialization instead. But I believe that one's done after the fact, after I have a coloring. So there is I don't have a coloring yet. I keep splitting until I get a coloring and recoloring pass. Now that I have a coloring, I look at, can I get rid of some of the extra moves by localized recoloring, where I preserve the invariant that I have a coloring and I maintain it after I recolor. Some of the recoloring games involve rematerializing, recomputing the value. Now, having said all that, there's also the game played around all the safe points and exceptional bailout paths where, by default, the register allocator is told that every de-optimization point has a completely free hand in what the registers look like, because the expectation is the basic block where you take the fail is extremely low frequency. So it's all free to spill anything you want anywhere. And in fact, it's not worth cleaning up the spills there. So like if I get extra spills in a deops path, I could make another round at the allocator to clean them out, but it's a never executed path. So I don't fucking care.
Oh, you mean you use like a save point, like a heuristic hint to say that this is a very low frequent path. So I don't need to care them very much.
Yeah, I will treat a safe point as a call instruction who allows all values to be passed in any argument register, including all stack slots and all regular registers, because they're actually labeled with the debug info. They're not following the usual calling convention. They're taking the debug info. So that just frees up again, what happens there. So you asked what I did about the inlining thing.
Yeah.
I did a basic block frequency smart spilling by doing these split instructions around high and low frequency paths. So after the allocator has failed and has done the forced first split, I then start to break up the basic blocks into high and low frequency regions. So I look for like the highest frequency block, and I expand nearby neighboring blocks that are high frequency until I see a sharp enough cutoff, and there's a heuristic that says sharp enough, and I declare you low frequency, and I grow these things out from their points until I come up with here is a set of high and here's a set of low frequencies, and those are the borders where I do my typical splitting the first go round, and that's
guided by the performance counters.
Yeah, that's cool. Sounds cool. Yeah, I never seen that before.
Yeah, the register allocator is one of the grossest looking, ugliest, giantest piece of code. It has been,
as long as it works.
and it works really well. Yeah.
So do you have a link to a place in C2 where you would recommend to start reading that code to get a sense of it, or?
Go find Chaitin.hpp in the C2 source code base. I've had C2 source code lying around, and we've had this brought up before. Let me go find it again. I don't have it lying on my head, but I can get there, I think, in a minute here. Here's JDK 7, but you can bet the register allocator has not moved far since JDK 7. Not the register allocator. Source, share, not cool, VM, Opto. So C2, my name was Opto, OPTO. Instead of C2, and that came from when I was a grad student. So that's still in the directory structure of JDK. The Opto directory name, that was me being a grad student naming my optimizer Opto.
What would you have would change if you can go back?
Oh, there's all kinds of shit I would change if I went back in time. Oh, dude, I'm a different person.
C2 wise.
Oh, C2 wise.
There's a great talk by this guy, Cliff Click, about advice for VM makers.
Yeah. Yes, there's that. That's not just.
I have watched it. It's cool talk.
Thank you. So Chaitin HPP is the guy. Let me give it a path here for you guys. And I'm not spelling it right here because I'm trying to not cut and paste my home path. Okay, so there's the core guts. Where's the giant ass comment? Somewhere in here, I'm gonna coalesce has got it. I have. This is really sad. You know, I'm looking at code I wrote 25 years ago and mostly pulling it out by name here. I am missing a giant ass comment that was all about the theory behind the register allocator. And I am not finding it right now. So you guys want to see reg mask and reg split and all.
Yesterday, I was ranting about the complexity of hotspot. I said that the hotspot was literally like a Linux kernel without driver plus GCC without document.
So
because C2 is like as complex as GCC, but there's no any document about that.
New splitting heuristic. This is probably a 25-year-old comment here. New splitting heuristic. So I can't find the giant good comment. You know, but here's, you know, things that look like this. So here's high and low split. You ask for rematerializing. Here's the code. This is in regsplit.cpp. So the register allocator is broken over 4 or 5 files. There's another comment. Split rematerialize. So there's, you know, things are going on in there all the time. I swear there was a giant ass big comment on the main design. I thought it was in Chaitin CPP. I thought it was an HPP. It might have been in CPP, and I'm not seeing it right now. Here's some good comments. Oh yeah. So you know. Here's a sample comment from Chaitin CPP. Register pressures track relative maximum values suggested for that platform, int and float pressure, relative other types to compete the same regs, and so on and so forth. Some Spark comments, some x86 comments, and so on and so forth. There's an ASCII gram table where I have some heuristics in here that are based on architecture. This gets into you have a 16 or 32 bit. Do you have split registers? No longer do we care about split registers, but the code's in there still. There's a lot of rematerialization code going on here.
So basically the term register pressure, just another name of cost, right?
Register pressure is the name of, these folks showed up here. Oh my goodness, they're an hour off. Yeah, fine. Hi, we're an hour into it, just so you know.
Okay, hey.
Yeah, so register pressure was my name for the count of live ranges, active live ranges at this point. And it was somehow relative to the set of available physical hardware registers. So that if you were wildly over pressure, we had to spill more eagerly. Like there was a thing where I was trying to cut down the count of major passes of the register allocator, and one way to do that was to recognize that this was a big compilation unit. I had way too many live ranges as I over registers. I was going to need that extra spilling pass. Might as well get started on early and break things up a little eagerly in an effort to cut down the times the allocator went 3 passes. It rarely went 4, and there was a panic flag somewhere that said if I went 5 passes, I was probably dead. But definitely, you know, 3 meant you were a big compilation and you were getting expensive.
3 minutes. 3 minutes for compilation unit.
Three passes. I'm sorry, what?
You mentioned that your register allocation may spend like 3 minutes.
Oh no, I meant three passes.
Okay. Okay.
It wasn't spending, typically not minutes. That we occasionally found bugs that something blew in squared on us and we got minutes and you're like, oops. But the register allocator has an n squared component. You'll build the interference graph and it's a dense big graph. It's, squared in the edge count, and that's where your time goes. So there's many thousands of lines of code in the register allocator, and they're subtle and complicated. And it's one of the major places where you could get performance where many other compilers failed to get performance because they were afraid to inline, because the register allocator would blow out.
Yeah, we have somewhat kind of an anecdote, a slightly different take on it. So in Falcon, for a long time, our lowering of save points was really simple. We would just spill everything which needs to be reported to GC, and didn't care to put it on registers and let it be read from registers. And we thought at first that, okay, this will be a performance bottleneck, and at some point we would need to do a better lowering of save points. But with aggressive enough inlining, hot save points were just rare, and we fixed that not so long ago. It works.
Hot save points, not DIAP, but hot save points.
Yeah, and even if it's just a save point poll, you would need to spill everything only on slow path if you take the save point.
Okay. Yeah.
So essentially, it's just a call. If you have a hot call, and you often inline it, so it wasn't a big issue.
If you have an off path for testing a bit, did you expose the diamond control flow?
Do you mean for GC polls?
Yeah. For a not a GC point, for a polling safe point, you do the poll test. If you pass the poll, you're happy, you're go lucky. If you fail poll, you take a safe point in and out. Did you expose that diamond to the register allocator or not?
Well, yeah, there was a diamond, and register allocator had to spill everything on this slow path.
On the slow path,
and then reread.
Yeah. For me, at that point, I had the safe points already. I could just say that you have free access. Register, naming all the registers as stack was enabled or not was free. So I just said all your registers are whatever you want, and then the register allocator would, in fact, be able to preserve everything across the boundary there, but he would just put debug info saying where things landed. So my off path didn't have to spill.
The reason we had to fix this is first, there are calls which we cannot inline. There are indirect calls. Okay, and we have to pay the cost of spilling everything before every indirect call. And second, we realized that with overly aggressive.
What was the thing you were saying that you couldn't inline? I mean, you're not a V call, or just compiler?
Yeah, if it's just a V call, megamorphic V call, they happen. We try hard to avoid them at all costs, and then we realized that we are very aggressive with inlining, but we have to pay the compile time cost. And if we take back on aggressiveness on inlining, okay, now we expose more of these calls, which GC save points, which have a cost associated by spilling everything. So yeah, at this point, we have it integrated with register allocator. Now register allocator can put the registers onto debug scopes, and GC can read it from there.
Yeah, okay. Yeah, the thing with safe points in hot loops is that you have to have them to have a break for the GC, and also they demand you keep alive a valid Java execution state in case you take the now depreciated exception that gets thrown by another thread at you, so that you have to acknowledge the existence that you're at some valid Java bytecode in the middle of running this hot loop, for which you don't really want to ever have to acknowledge. So you want to get rid of them, because they're the debug info, even computing it, never mind spilling it, even computing it, it's costs. And that gets me into like I did unroll and jam for some of these loops as a way to reduce the count of save points. And I guess the theory now is that you can't throw an exception anymore across threads.
Oh, this API is deprecated, but at least in Hotspot, the notion of deopt point and GC save point, it's still intertwined, and it's not that easy to separate. Like we do want that, yeah. So sometimes it's convenient to have an ability to have a GC save point, but not a deopt point.
Yeah, that's what I'm saying. I'm asking because as soon as you do that, all you have to do is flag the oops and verify you get them set correctly. Whereas the deopt means you have to carry extra information, which is the the bytecode state, which includes indexes for loops that you strength reduced, and there is no index anymore.
Well, one thing we do to somewhat reduce the cost of it is if there were no side effects, the state we would keep for the save point would be some earlier state in the bytecode. So when we deopt, we would re-execute all the code which didn't have side effects.
Yeah, no, the reason I put the deopt as just a call in the graph is the allocate. The optimizer can reorganize however it wants to reorganize. So things that don't have side effects are just like math ops. The optimizer shoves them all around however it wants to. They go forward, they go backwards, they go down, get recomputed if necessary at a safe point or whatever. Whereas memory state, I wouldn't allow to move around the safe point.
Well, so I guess it's the difference how it is represented, because yeah, I think with floating nodes in C2, it happens more or less naturally.
Yeah.
With explicit control flow, with explicit schedule, we have to do some work to move this around.
Yeah, that makes sense.
Okay, let me change the subject a little bit. What are your sentiments about functional programming? Why in recent years has become much more mainstream? Why has been failed before? And where will we go from here?
Do we want to give the people who just came in a chance to introduce themselves first before we go down that
Okay,
rabbit hole?
okay, cool.
Gabor, you wanna 10 seconds? What do you do?
Hi, I'm Gabor. I'm working on static analysis for C++. Currently, I'm working for Microsoft, and previously I interned for Apple and Google.
What kind of static analysis?
Mainly finding bugs like lifetime issues, use after free, and yeah, stuff like that.
Yeah. Okay. And Rika, Rika, did I get that right?
Yeah. Hi. Yeah, Rika is fine. I come from the same university as Gabor. I'm also working at Microsoft at the moment. I recently joined the Java engineering team. That's how I know Kirk. Yeah, I also have a background in C++ static analysis. I'm still a PhD student in that topic. And I did a Google Summer of Code with LLVM, with the Clang static analyzer team, and a summer internship at Microsoft with the Visual C++ backend team.
What year PhD?
It's a like bug finding kind of static analysis for C++.
Okay. Yeah, I was asking what year, but no, I really wanted to know what was your topic. Oh, sounds good. Well, okay, so here you have a pile of compiler experts. You have any questions?
I myself would prefer to just listen in the beginning because I'm really not confident, but maybe later.
Yeah, I'm a horrible monster and I will bite your head off. You just ask me here. No, ask questions, but lurk is fine too. Okay, we can go back to functional programming. And I would claim that you said it had failed in the past, and I claim that's not correct. It has been slowly growing very steadily for a very long time. Haskell is quite old and has only ever grown in popularity slowly.
I will accept that, yes.
Okay.
I would also say that I would say the influence of it is perhaps even greater than the use of the language itself. Like,
what are the main effects you think that functional programming has to offer?
Oh,
to Yorick.
Oh, so I think there's sort of two sides to that. there's the sort of, let's say, the research impact that it brought with it, and the let's say the practical aspects, like perhaps certain techniques, whatever. In the research, we ended up with garbage collections. We had Lisp and all the stuff that, well, yeah, Lisp machines, tons of things. In terms of like practicality, I think you see in a lot of sort of the style that you have for libraries for dealing with iterators, transforming data and such, where you have these more functional interfaces, opposed to the more
maps are
yeah,
yeah,
opposed to the more
yeah, that was my
approach.
next question, but I will ask it later. Sorry for interrupting. Yeah,
it's all good. So the other piece of the functional programming is the first implementations had really bad performance relative to the imperative. And so you had to be in a domain where you either didn't need the latency or the throughput. So
is it the optimization, the problem, or the technique, or both, for ending up with the slow code?
I think there's some of both. There's the love it or hate it, the imperative thing makes you think about the state of memory, and actual hardware, like what fits in your cache is 10 to 1,000 times faster than what didn't, right? So as soon as you're not thinking about memory, and then you start saying, hey, an integer should have a wrapped around, should be boxed so I can treat it like an object like anything else. And suddenly your integers got slow by 10x, and integers are everywhere. You can't not do that or whatever. So you pay a bunch of speed. People got better at implementing that, but maintaining the strong semantics of the functional language with a primitive was hard to do. And so they usually gave up at either the stronger semantics or they gave up on performance. And like I said, it's gradually been getting better, but it's still not perfect by any means.
So how much higher in the abstractness has the functioning technique goes? Some category theory, some monads, some here and there.
Oh, I think we'll build as we go. We're always, we love to see we're standing on the shoulders of giants.
Yeah, but
the toes of the prior giants.
Math is already there. It's been decades.
Yeah, right.
At least, yeah.
Yeah.
But how much abstract we should go before our code has been going terribly slow?
Oh, no. That's a different one. That you asked, what is the usefulness of a abstractly theoretical model versus performance? And that varies entirely by usage case. If I am racing to go get my ML speech recognition app on my phone to market with the guy down the street, and I win and performance sucks, but it's fast enough to get there and it's good enough, it didn't matter how slow it was or inefficient it was internally. If I'm drinking from the Twitter fire hose to come up with sentiment analysis for the next high frequency trading thing, it totally fucking matters how fast it is, right? So there's different uses in different domains. Sometimes I code in Python or fucking shell script because it's quicker to get the job done.
Yeah, but these days, once we get functional mainstream, the theories has become much more abstract. There's monas, there's zippers, there's category theory, flying terms around here and there, and that just carries the developers.
But I think the core lesson there is that all the stuff already exists. We are just now giving names to things that already were there for like 50 or 100 years. So it's more like a categorization of existing ideas. And I think the difference is this kind of categorization allows abstraction without indirection, which is, I think, or in my experience, a large difference to object-oriented programming, where almost all kinds of abstraction also introduce some level of indirection.
Yeah, if you plan yourself correctly, you should be able to do them both at the same time. Garbage collection has been around for 20, 30 years before Java picked it up, right? It had to sort of bake. And then a language came along, they integrated it in a smooth, convenient way and had everything else done right. And then you get to take off and go.
By the way, sorry.
Yeah, go ahead.
In case of static analysis, there are a lot of inspiration coming from functional programming and functional languages. And in a lot of cases, the techniques we pick up from the functional world actually increasing the performance. And the reason is that the way some static analysis works is they have a representation of the program state that has some representation of like binding memory locations and values. And when we are evaluating a statement in the program, it only changes a small portion of the program state. And using persistent and immutable data structures that came from the functional programming world, we can represent basically only the deltas. So we do not need to copy the whole state and do the modification, but we have a more persistent data structure. And using those programming concepts can really make a big difference for static analysis tools.
So what about an approach that is some kind in the middle, like rest, reason, your structures? Of course, it has immutable variables or what they said, but the rest has some kind to simulate that with rest borrow checker, and behind the scenes, it compiles to a mutable state machines. It throws out your abstractions or it compiles them away, so your code becomes more efficient. Will this be a viable approach in the near future to compile all the functional abstractions away?
That's what I'm trying to do with AA.
Yeah. I was just I will ask you, but you answered.
I have, full first-class closures, and 99% of the time they disappear. Having said that, I don't have enough code to actually, make that claim stand, but that's the goal.
I was surprised when I was first playing with it and it was like, oh, you can call things with Lisp style calls. That was surprising.
Yeah. I'm not even playing with it. The last 2 weeks I've been doing this damn SQL database optimization hack for these folks, and I want to get back to play with AA. Yes, it'll take C style. In fact, it is semantically ambiguous. All function calls are done Lisp style, but you can hand a tuple over, which follows the call site, and the tuple will get syntactically sugar unpacked as arguments. So it supports both C style calls and Lisp style calls equivalently with the same mechanism under the hood, and makes it disappear and become free, if you will.
I guess my main argument with like the benefits of some of these functional and just generally moving to more abstract solutions is that it depends on the scale of the problem you're trying to solve. If you want to solve the kind of thing where you could have written the assembly code to solve it, you can write very low-level assembly-like code that will give you a lot of performance.
Yeah.
You can't really write the Google search engine in assembly. You need some higher level. And with the procedural stuff, as we build layers upon layers upon layers upon layers, we get to the point where we can't handle that complexity. So we make very inefficient things. So like SQL fundamentally is going to be a lot slower than if you wrote the handwritten assembly to do those data retrievals. But it turns out our SQL databases are fast because for the most part, most people can write a SQL statement better than we can write the assembly to implement the query plan of that SQL statement.
The difference in abstraction layers is that periodically you get to change your mental model and write it in a way that solves the problem in a much faster way. So while running SQL versus running the equivalent C code is obviously much, much slower, periodically I can stare at the SQL, do a transformation on it that I couldn't do in my head in C. And now write a query is way the hell more efficient. So asymptotically more efficient, and thus get a faster answer out. There is a place in the world for SQL-like declarative languages because they let you think about the problem in a new way.
I think there are no really equivalence between a SQL statement and the C code snippet in the sense that a SQL statement does not have the have an algorithm associated with it. It can use runtime statistics to choose how to do a merge join or something like that. So basically, when we think about the equivalent C code, we do not think about all the runtime decisions that are being done by the database engine that is
C code. You immediately go to the point of an implementation, and SQL says there are many implementations. Perhaps I can find a better one, right? And you go for C code. You said here is an implementation. Yeah.
Well, yes and no. Even with the C code, you have this as if rule. I may have said 5 times 10, but the compiler can go through and say, I'm not going to do 5 times 10. I'm just going to put the constant 50 here. The difference is that SQL didn't pin down the algorithm nearly as aggressively. So the as if just has a lot more flexibility.
Has a lot more flexibility. And then, of course, it has a lot more room for getting it slower or harder to make it go fast, too. So both these go both ways. Yeah, I've been playing with SQL in the last 2 weeks, obviously. I have a lot of SQL queries I baked down into Java code, and I can get them the baked down versions to run as fast as the state-of-the-art best breed implementations floating around. So I'm tying with the world record.
So the core is how efficiently we can compile abstractions away.
Right. Yeah. How best can you boil it down? SQL starts from a higher place and gives you some wiggle room. But after you drop it down a layer or two, the SQL compiler folks do not have a classical compiler head, and they need to hand it off to somebody who takes it from there and drops it again, as you said, to where the compiler can choose 50 times versus 5 times 10, or to spill a register or not spill a register.
So we generally, with functional programming, we headed about a code which is more composable. I believe that the core concept functional programming is trying to sell is about composability and the reason about your code and how the stuff comes with it. But we have to give up a lot of the mutability. Local mutable state is fine, but not global.
One of the things I'm trying to do with AA is to allow functional programming and mutable state. That in reasonable ways to get out mutable state, because there are big hard problems for which mutable state is, you must either go there or they're just super the most efficient way. Just got to be mutable. Okay, fine. Functional programming, as you said, composability, I love it. Right? And now, isn't there a way to go have them both? I want my cake and eat it too. I'm looking at the 12 rules. Oh, this is this is what it is to be a database. Fine.
Yeah. I never have a chance to do some kind of circle optimization. Is this similar like the conventional compiler optimization or something different? So what's the basic unit of circle optimization? Is it an expression or statements? Because if it's like an expression, it's totally different from like a C or C++ compiler.
SQL is a declarative, not imperative. So it describes the shape of the answer without telling you how to get to the answer. And then the bridge you have to gap, it can be big. So as for instance, a simple query might be, go find triangles. I have a column, an array of pairs. Go find all the triangles where the A to B, B to A to B in a triangle. Okay, as a SQL query, I simply say, give me the set of things where A has an edge to B, B has an edge to C, C has an edge to A. And I walk away.
And it will have to join them, of course.
Well, as soon as I said that, I have 3 joins. I have an A to B column that joins with the B to C column, which joins with the C to A column. I get 3 joins. And now what's the most efficient way to go implement that? Well, there's a bunch of algorithms you can go do to go implement that, and they have different complexities and different runtimes and whatever. And I did one in H2O that has its strengths and its weaknesses, and it looks like I'm on par with everyone else who's doing it really, really fast, but it's not asymptotically optimal, because the asymptotically optimal one says I can find all these triangles without going n squared, and I'm doing an n squared algorithm. And it's a fucking tiny, tiny, tiny constant, and my n squared with tiny constant is beating all the fancy algorithms. And that's the general theory here. But there is a point where the n squared should win, and I should have a better algorithm that doesn't go n squared on me. And the SQL query didn't say I had to be n squared. I reached for an algorithm that was n squared, but there was no requirement in the description of the SQL. So that's just a sort of a trivial one. You get lots and lots of these things where somebody says, I'm looking at a sales report of blah, 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 and I want to go find all the people who have the following criteria and all my stores that are selling more TVs and less of this and more of that. And I want to rebalance the East and West Coast TV sales of the last 3 decades. And they describe the problem, they describe the solution they want, the answer they want, but they don't tell you how to get there. And then the SQL optimizer turns that into a pile of imperative code.
Yeah, that was what this is. I believe this is one of the main things of the functional programming too, declarative instead of imperative.
It's more functional is more imperative in the sense that it really has an ordering. Ultimately, I see what you're saying. You're saying it's a if it's a true mathematical abstraction, you're right. It doesn't have any ordering. It can go any way you like. And the implementations as we see them today all immediately boil down to a straightforward execution of a particular variant of a Lambda execution machine, and they have a therefore go straight to a semantics. You get a prologue and you get a version that says I can pick the different orderings, and in fact I want to have an optimizer to think about it before I start running the prologue, whatever the standard data log execution engine is.
Yeah, I was going to ask if anyone here had done a lot of prologue or data log work.
Wait, I knew a new word today. It's a declarative programming language. Is this kind of like a functional or like a totally different from functional language?
It's a different it's orthogonal.
Orthogonal, okay. So basically there are 3 types of programming language, imperative, functional, and declarative. Can I say
declarative? Okay, I'm trying to find a good wiki articles. If you search for declarative versus imperative programming, a lot of articles come out. I don't have one I like.
Declarative in an essence doesn't say how to do it.
Yeah.
Declarative says what to do it, but not how to do it. Imperative is a recipe, like a step-by-step to reach the end.
Yeah, declarative is I want a cake. Imperative is grab 2 cups of flour, throw it in the blender, grab some baking soda, grab some salt, grab some right. And
they look at they look at the problem from the opposite perspectives. One is from the bottom up, the other is the top down.
Yeah.
But it sounds like eventually you compile the circle statements into some sort of imperative language. I believe it's like a low-level C or something like that.
Yes. You have to do something. You have to have an execution engine in the end, and it runs on a piece of hardware which is imperative. So you have to boil it down to imperative. And one of the problems that has plagued the functional programming community is the inefficiency of the typical boiling it down to an imperative language. And we have slowly gotten better at boiling these things down where the inefficiency matters less. The SQL folks said, we'll also boil it down, but we're solving it and we stick our heads only in solving the high-level problem version. We don't get wallowed down the details, which makes the problem space suitable for people who are solving business problems. And so these are not programmers, right? So we have addressed an entire generation of business people who solve their problems by saying, what is the average inventory lead time on my TVs and warehouses, and am I going to run out for the Black Friday rush? And that's an entirely different head, and these people are very, very useful, and they are not programmers.
I think the point Gabor mentioned regarding persistent data structures is really a huge thing that needs more widespread use to make programming in that style efficient. I think that's largely a problem of adoption, or not a problem of the technology not being there.
No, I'd say that's not the issue. Or at least I have been doing immutable data structures and hash consing by another name for 40 fucking years. The tools are easy to implement yourself. there is a sweet spot where they solve a certain class of problems really well, and there's an overhead to using them that is really high, and so they are no good at another class of problems. So it is not that they should or should not be adopted. It's easily available to go write hash counting things. Everyone who's ever implemented a standard data structure can go implement a persistent one. As soon as you get out of the next generation of class at college, it's not that hard. That's not the issue. The issue is, Prolog's a declarative language. The issue is there's a performance cost to these things that is non-trivial, and you have to be in the domain where that's okay.
I think you also have to solve problems in a different way. It's if you're trying to solve imperative, if you try to implement imperative solutions with persistent data structures, it won't be pretty or performant, but sometimes it's possible to reformulate the problem or to have it to look at it from a different point of view, and then things become viable.
Sometimes it's possible. Sometimes
sure, absolutely. But sometimes I just see it's like you have like new languages like Swift that have like persistent data structures in the sense that they are like reference counted, and based on the number of references, they either mutate their arrays in place or do a copy on write, which is like incredibly inefficient, but they hope they don't have to do it that often.
That's not right. That's the implementation, not the coding style. There are times when the coding style for using a immutable structure makes sense, and there are times when it simply will not work. And then when it does make sense, there's an efficiency concern. Like if I went to a big shared web server, I'm taking URLs from all comers and I'm caching most of them and handing them back out, the JDBC driver, any of these things. I want a big shared memory concurrent cache, and your immutable structures do not fit in that paradigm.
Yeah, sure. What I have more in mind is like if we want to have like efficient operations, then we like can't settle with persistent data structures that are basically copy and write arrays. So we have to consider like a hash array mapped tries and bankers queues and whatever. But
big claim to fame was they made it possible to have structures that were mutable only when needed and immutable when needed. Like at all, like you could actually have a language compiler support to say it's immutable, or it's mutable where I need it for efficiency, and then I can go right back to being immutable again.
Which language was that?
Rust. That's in my opinion, that's their major, and it's a big one, big progress.
Yeah, I think it's operating on a different level. I think there's like one kind of performance that's gained from persistent data structures that live in libraries and actually are like optimized with clever code or better algorithms.
Right.
And I think the
JODA.
things Rust or Swift do, it's like it's a different style of programming. It's like you declare the variable mutable, and suddenly all the insides of the variable are mutable too. I think it's really different, because you still you can switch off the mutability. Either it's immutable or it's mutable, but you can't say, okay, it's immutable, but my mutating operations are reasonably fast by using persistent data structures instead of copying everything. And I think there's like a fundamental difference. I think it makes sense to think about combining these tools, but I think they can't be, they are not the same.
They are not, but I want to make sure we're talking the difference between implementation and coding style, right? There's the knowledge that it's purely functional, which is what you get out of immutability. And then I can think about it as being purely functional, which reduces this huge operator overload in your head, huge thinking. That's the gate. And then immutability is a complicated thing to get right. unless you're single threaded, and Rust lets you define the ownership much more precisely than other people. So you do get a chance to run it as it's mine and I can do what I want with it, and it's very efficient. And then there's also the notion of it's immutable and shareable, and everyone can look at it, and diatomic from the Clojure community, that kind of stuff, where I do this shit all the time in AA too. In the implementation of AA, I have immutable types, and I mutate them by doing the minimal copy on write, however it's done under the hood, and I code at a higher layer. I just have types, and they are, for all intents and purposes, immutable, and I reason about that level, and that is the gain of being immutable, the thinking.
Yeah, the persistent structure has its strength points, but we should not forget that the hardware thinks about it mainly mutably. And that's why the while loops and the register and the prefetching of data, it's so fast that persistence will hardly keep up. But
the efficiency cost for many of the immutable structures is because we copied, you burn more memory, which didn't fit in your caches, and every time you cache miss, that's your costs, right? You count your cache misses, that's your cost to your program. When I was a kid, you counted instructions. Then there was a time when you counted, page faults. Now you count cache misses. And that means you can't allocate furiously. And that means things that do copy on write have a cost. So back and forth, it depends on what domain you're in.
Yeah, well, one of the main things, the functional problem, is allocating a lot. It doesn't be much careful when it allocates.
Right. And that's one of the things I'm playing around with AA is can I arrange for it to look good, and you can write C-like code, get C-like performance, but if you want to be functional, you can do that too. That's
one of the things I found inspiring reading about Pony. It's like, okay, we've got a bunch of references hanging out here. Let's actually think about, is this something that exists only in me? Like, is this the unique reference? Is this a concurrent reference where everything must be in the same thread of execution? Or is this a global reference that, like, somebody asynchronous to me could be holding the same reference to the same thing? And
wailing away on it. Yeah, I want to be able to do asynchronous concurrent coding in a reasonable way, and I want to have a way to say, no, it's local too. I've done a lot of this stuff all my life, and as soon as you go asynchronous, you have to start thinking about the problem in a different way.
Or you could go the Erlang way and say, let's turn every problem into a distributed systems problem on the off chance that we're going to need to do it on more than one computer at some point in the future.
I've been a long time down that path. Yes, exactly. And I have a lot of problems I've solved that way by starting, okay, we're going to be distributed. And holy shit, you have to think about it a different way now. All right, fine. All right, we're like headed up to 2 hours, an hour and 45 minutes. I think we've beaten this one down pretty hard. Anyone else want to add anything here? I'm going to wrap it up. All right. Well, it was good. As usual, I learned something new. In particular, JODA time got moved in the JDK 8. I swear maybe I've heard it in the past, but now it's been beaten into my head. And I got some reading to go do too. So that all looks good. Okay. This is going to go up on Twitter. I don't know when. This last week I had a vacation, so I didn't get around to it. So hopefully faster this go around. And see people next week.
Sorry, I have one quick question. Will the chat also be available somewhere with the links?
Yes.
Oh, wonderful.
It shows up on the YouTube comment section. Yep. Okay.
Great.
Yep. Bye.